we're all very excited, well, I'm very excited at least, to hear from Yin Zheng, who received his PhD in EE from Tsinghua University in Beijing, China in 2015, and is now employed at Hulu Research over in Beijing, working on recommendation systems and deep learning. And this talk he's going to give, CFD, he actually presented at ICML a week ago. I attended the talk, I thought it was very good. Too short, so we're excited to see the elongated version of the talk. So please join me in welcoming in.
Hello. Okay. Thanks, Joe, and the very nice introduction. And today, I'm very glad to introduce our. I'm an associate researcher at Hulu's recommendation team. Today, I'm very glad to introduce our recent progress on collaborative filtering, which is called CFNAME. This work was joint work with my colleague Bang Sheng Tang, the second one, the Wen Hui Ding, and Eric Zhou, our boss. So, before I start my talk, I just want to clarify that about 2 days ago, I found a paper which is quite similar to my paper, but I didn't aware the existence of that paper, so I just show you that one. So this one. This one is a paper that I never know I didn't know the existence of this paper, but this one is my paper. I just searched with the title of my paper, but I don't know why Google put this one in the first. And so today I found a guy to attend this attend this workshop. He bring this paper with him, but I will tell you that is totally wrong. And actually, I think the main motivation of this paper is the same with my paper. They also try to use the NADE model. The NADE is short for the neural autograduate distribution estimator. However, the guy sent this paper to ICDM about 2 years ago. But the paper was not accepted. So just put this paper on his website. But so after I know the existence of paper, I'm so nervous. Maybe they are the same. So I have a quick look of this paper. Finally, I found the paper. Although we use the same motivation, but this paper didn't use any. They are not the same at all. They didn't use the trick, and the performance of that paper is not that good. It only compared with the RBMCF, but we compare with the richness in the art, and we also use a lot of trick to improve the performance. So I think you will learn more by my paper than that paper. So just to clarify. Okay, so I will start my talk. This talk. This is the outline of this talk. I will first introduce the motivation and the related work, and then I will introduce the basic model of CFNAME and the 2 tricks to improve the performance of this model. One is the sharing parameter between different ratings, and the other one is to factorize the big connection matrix by the product of 2 low-rank matrices to have better scalability. And I will also introduce an ordinal cost, which is quite useful in collaborative filtering. And to my best knowledge, we are the first paper to propose this kind of ordinal cost for the CF tasks. And I will also tell you how to extend the CFNAME model to a deep model to have better performance. And in the experiment parts, I compared our model with the other state-of-the-art baselines on some explicit feedback data set. And I will also show you the visualization of the learned model and give you a quick overview about what is the feature work we are going to do in Hulu's product. Okay, the motivation. We all know that the modern online service such as Hulu relies highly on the recommender system to help user to identify the item that they might be interested in, and also provide a personalized experience. The most popular and the successful technique to building a recommender system is the collaborative filtering, which predict the user preference based on the user's past behavior and the decision made by the similar users. One of the basic assumptions behind the CF is that the user preference will not change dramatically in some time. CF is also the core of Hulu's recommender system, and this technique has been widely used in our product. For example, this is the page of the homepage of Hulu. Actually, we have provided a personalized homepage. That is the trees is different for different users based on your preference, and also we have developed the personalized must-have is this one. And it's very big and give you big impression about what is trending on Hulu or what is the recommendation based on our prediction. And so that is also personalized, and also the watch list, the top picks, and the rated shows. A lot of recommendation products use the CF techniques. Although there are a lot of CF techniques, CF methods, most of them are based on the matrix factorization. If you search the CF on Google, you will find some like the SVD or SVD++, the BIOS matrix factorization, the probabilistic matrix factorization, Bayesian probabilistic matrix factorization, and so on. The most successful and famous neural network-based CF techniques is the RBM CF, which was first proposed by the Sarakuninov, the Min, and the Hinton in 2007 at ICML. In that paper, they used the RBM to model the probability of the ratings, and it works well in practice and also well in the Netflix challenge. To my knowledge, there's a tutorial two years ago at KDD by the Netflix guys. He confirmed that they use a combination of the matrix factorization and the RBM CF in their product. They said in the tutorial. And but you know the RBM CF is based on the restricted Boltzmann machine, so he had to relies on the contrastive divergence to optimize the model. So it will be very slow and not very accurate. So with the recent progress of deep learning, more want to know whether we can do even better. For example, last year people had proposed the auto-rec, which is the CF techniques based on the autoencoder. And this model works quite well in the Netflix dataset and also the other Moonlight dataset and so on. So that is also one of the baseline for our paper. For the CF-NATE, as it said in his name, is a NATE-based model. NATE, as I have mentioned in the beginning of the talk, is the short for the Neural Autoregressive Distribution Estimator. And it is a tractable distribution estimator for fixed-length binary vectors. And it was first proposed by Laoshi and Murray in 2011. In this model, he factorized the probability of the vector by a product of a series of conditionals. And each of the conditionals is modeled by feed-forward neural networks. And all these neural networks will share the parameter. Actually, the NATE model is quite efficient. The complexity is about ODH, where the D is the length of the vector and the H is the number of hidden units. And it works very well in practice for the high-dimensional data. NATE, there are a lot of variants of NATE model. For example, the real NATE model, it will extend the NATE to model the vector of the real data, not the binary data. And the DocNet model, he used the net to model the background word representation of documents. And we also developed the supervised DocNet model and deep DocNet, which add the supervised information into the DocNet model and use that model to do some work. For example, the multi-model data modeling, we can combine the image and the text together to have a unique representations and to do some image classification task or the image annotation task, and also to extend the model to a deep version or extend the original name to a deep version, the deep name model. And we also use the name model to do fixation tasks. That is, we can learn simultaneously the what to look and where to look. We model the recognition as a sequence of fixations. And actually, the model can learn very meaningful policy. That is, if you try to recognize the expression of a face, and here you find, the model will focus on the mouth or the eyeball to see whether you are smile or whether you are angry. And if you try to model, try to recognize whether the face is a male or a female, you will focus on the other parts of the face. As the name model has achieved very promising results, we also want to say whether we can use the name model for collaborative tasks. That is, so I will introduce the DataSci model. So the background is the same. We have n user and n movies, and for each user, he will rate several of the movies, and the ratings is the integer from 1 to k. And then we can represent the user as the ratings given to the movie. For example, this user, he rated D movies, and we can represent the user as the vector of these D ratings, where the O is the ordering of the movies or the ratings, and the MOI is the ID of the movie, and the R is the rating. So if we can write the user in the vector R, we can represent the probability of the rating in this way. By the train row, we can factorize as the product of the conditionals, where this one means the previous I minus 1 ratings. So similar to the original model, we want to model each of the conditionals with the feed-forward neural network. For example, this is one option. We can try to model the probability of the users give a movie MOI a K rating given the previous I-1 ratings by softmax, where the SMK is the score indicating the user's preference to give a rating, to give a movie MOI a K rating, and based on the previous I-1 ratings, that is the context information. And the SK can be computed in this way, where the hidden representation H is computed in this way. The G is the nonlinear function, C is the Bayes. If the in the context, if the user gave a rating MOJ, R MOJ rating, we just add the corresponding column into the hidden representation. So, as I have mentioned about the order, so the order of the model should be prefixed. For example, we can use the timestamps of the ratings to order the ratings. But in practice, we found the random order works well in practice. Actually, different orders will induce different instantiations of the self-named model for the same user, and that is also the key to extend the model to a deep model. I will introduce that later. Okay, so now we have modeled the probability of the user. We can train the model by minimizing the negative log likelihood. Right. After the model is trained, give for unknown rating M star. We can compute we can predict the final ratings in this way, which is the expectation of the ratings computed by this model. So in this figure, that means given the 1, 2, 3, 4, the user rate four movies, and we add all these ratings into the hidden representation H, and use the H to compute the probability of the rating for rating K for M star, and then take the expectation. Usually, different users will give different number of ratings. So, similar to the RBM CF, we build a different CF-named model for different users. That means for each model, there's only one training case, but all these models will share parameters. They will have the same number of hidden units, and they will have the same connection matrix, W and V, and the same activation function. All is the same. So that is the basic model. So in this model, if you see these two equations, you can find that we actually gave different parameters for different ratings. For example, this movie, we give different ratings. We will have different parameters for this one, and also to compute the score of the SMK. That will induce a lot of parameters. If some ratings of the movies appear rarely than the other one, for example, the Forrest Gump, I think all of us, maybe all of us, like this movie. It's very popular, and so maybe the rating for the Forrest Gump will always be 5 or 4, but the rating for the 1 or 2 will be very less. So the corresponding parameters will be less optimized, right? So, to address this problem, we propose to share the parameter between ratings. That is, if the true ratings is 4, and we will use the parameter for 1, 2, 3, 4 together to compute the hidden representation. So there's a summation here. And you can understand the this trick as is a kind of regularization. We want the model to explain the data using as many parameters as possible. So in practice, it's quite useful, and I will show this point in the experiment parts to using the shared parameter trick. But sharing the parameter between rating will not reduce the number of parameters. When we deal with large-scale data set, for example, the Netflix data set, in this configuration, it's not very huge. It's not very huge. The hidden size is only 500, and there will be about 90 million free parameters. Although we can use the VDK or the dropout to avoid the severe overfitting, but training such a big data, the neural network will still be problematic. And so, inspired by the RBM CF, we propose to factorize the large connection matrix by a product of 2 low rank matrices. And if we do this way, where the J is the rank of the low rank matrices, and we have only 9 million free parameters, that will be much better. So after introduce the two trick of the basic model, I want to emphasize the ordinal cost of the CF tasks. So what is the ordinal nature of rating data? That is, if the true rating, if the user gave a show, for example, this is a Hulu show, gave a 4 star, and the user preference for rating 4 to 1 should decrease the monotonically, and also from 4 to 5 should also decrease the monotonically. There's only one peak. But if we use the regular softmax to optimize the model, maybe it will happen that the true ratings is the highest among all these ratings, but the rating 1 might be higher than rating 2. So the softmax will not preserve the ordering of the preference. So that may be make the performance worse. So consider that we propose the ordinal cost, which is we compute the probability of the conditionals in this way. Actually, this one is in the learning to run perspective. that means that is the probability of the rankings down, y down, and y up. That is the k is for the k rating is higher than k minus 1 rating until 1, and k rating is higher than k plus 1 until k. So we named the cost induced by this kind of conditionals as the ordinal cost, and named the cost induced by the softmax as the regular cost. So we can use the hybrid cost, right? So so in this way, where the lambda is the weight of the ordinal cost. I should mention that there are also several works to use the ranking laws in the collaborative filtering tasks. However, all this work will focus on the ranking of items, or ranking of the users, but not the ranking of the rating data. So that is the main difference with the other methods. Now, so how do we extend the model to a deep version? So as I mentioned before, we use a random ordering of the ratings to model the joint probability, right? To optimize a model with a statistic sample order comes down to minimizing the cost of the expectation of the cost over all the possible order, right? So by doing this, that means given a context IMAX1 ratings, the model should perform equally well for each of the conditionals in the remaining sites. Since for each of the item there is an order that the corresponding item appears at position I. So instead of sampling complete ordering over all the items, we instead sample context of the I-1 ratings and perform an update of the conditional using that context. So in this figure, that means if the user rated 4 movies, and we randomly split the ratings into 2 parts. Maybe one part has 2 ratings and the other part has 2 ratings also. Or maybe there's nothing in the input part and all is in the output part. Or maybe 1 in the input and 3 in the output. And that is the context. And we use that context to propagate into the model. And so the cost function can be rewritten in this way. If you see the paper in the supplementary, there's details about how to derive this kind of function. That is given the sample of context and using the input of using the as the context and to predict each of the elements in the next in the other split of the rating data. So by doing this, more hidden layers can be added into the regular multiple neural networks because we do not need to sample to predict the probability 1 by 1. The input is the same size. So the complexity is the OK d hat h plus the h square L, where the d hat is the average number of ratings that the users, and k is the number of ratings, and h is the hidden size, L is the number of layers. I will show the complexity in the experiment part, the running time. So now I will show you the experiments. In this experiment, I just want to show the advance of the self-named model. So I test the model on 3 public benchmarks, and the movie length 1 milli, movie length 10 milli, and Netflix. The item-based self-named and user-based self-named. So the user-based self-named is that we model the probability of the users, as I mentioned before. But the item-based ones is we model the probability of the items. We just change the role of the movies and the users. And usually people will find that the item-based ones will perform better than user-based one. But there's a lot of the number of users should be higher, much bigger than the movies, so it will cost a lot of computation resources and the memory. So there's some cost to use the memory, the atom-based ones. And we use the RMC as the measure metric, and which is also used in the other baselines. So first we will show you the impact of the ordinal cost and the sum parameter trick. In this figure, in this experiment, the hidden side is fixed to 500, and we use the weight decay of 0.015, and we use the Adam optimizer to optimize the model, and the learning rate is fixed to 0.001. If the training, if the validation error didn't decrease more than, I think, 60 epochs, I will decrease the learning rate by 4, and until the learning rate is smaller than some value, maybe I think it's 0.0001, something like that. So in this figure, the x-axis is the weight of the ordinal cost, and the y-axis is the test RMSE. From the figure, we can see that the performance of the self-named model with only the ordinal cost performs better than the hybrid cost and also the regular cost. That shows the advantage of the ordinal cost. And also the gray line is the self-named with the sum parameter trick. And the red line is the self-named, the basic self-named. We can see that the sum parameter trick can improve the performance significantly. So in all these left experiment, I will only use the ordinal cost and the sum parameter trick for each of the data set. So now I will compare the self-named model with the other strong baselines. The configuration of the experiment is this. We use the hidden size is 550, 250, 500, and 750. The weight decay is cross-valid on the validation side and selected from the 0.015 and 0.02. And the learning rate is this rate is cross-valid on the validation side from these three values. Let's first look at the table. The atom-based self-named with sum parameters and one single layer performs comparable with the other state art, that is the atom-based auto-write and the local low-rank matrix approximation. And with two layers, and the model can even get better performance. And for this table, I use the hidden side equal to 500 units because the atom-based auto-write also use the same configuration. And for this figure shows the comparison of the single layer and the double layer with respect to the number of hidden units for each layer. And we can see that the performance of the deep model performs better than the shallow one, and the hidden size can improve the performance if the hidden size is larger than 500 units. Movie length 1 million is a quite small data set. We also want to see the performance on larger data set. For example, the movie length. The configuration is the same, but as the movie length is a bigger data set, we do not want to waste a lot of computation resources. So we just use the user-based self-named model. And we use a factorization trick, as I mentioned before, and the J equals to 50. The learning within the two match parameter, hyperparameter, the learning rate is fixed to 0.005, and weight decay is also the 0.015. From the table, we can see that the user-based self-named model can beat the item-based ones. Actually, the item-based auto-write, did I mention that one? Is quite big for the first row. It's much worse than the item-based auto-write. But our user-based one already beat these methods. So that means our model is much powerful. If I just want to use the item-based one, I think the performance will be even better. And also on the net-free data set is much bigger, and we use the same configuration with the baselines and the J equals to 50, and learning rate is 0.05. As the data set is quite big, we do not need to use a large weight decay, so the weight decay is set only 0.001. And from the table, we can also see that the user-based CFNAME model can already beat the other ones significantly, right? So from the auto-rec model is proposed in last year, and the last state of art, which is proposed in 2013, there's only 0.01%, but our model improved the performance much better. Okay, so this is the complexity. I showed the number of parameters and the training time and the test time. For the movie lens 1 mini dataset, I didn't use the factorization trick, so the number of parameters is higher than the movie lens 10 million and the net-rate dataset. Because the movie lens 1 million is quite small, we do not need to use the factorization trick. And we can also see the different layers will not enlarge the training time significantly. So that means the deep version is very efficient. But the training time is a little bit longer for if the size of the dataset increased, right? So that is the main reason is that we do not have a very efficient implementation of the model. You know, on the GPU, we usually want to feed use the batch of the input, right? So we want a mini batch to put the mini batch into the model to train the model, because we will get some speed up. And but different users will have different number of parameters, so the size of the mini batch would be very different. So to use the mini batch, so we didn't use a very efficient implementation. That is, we represent samples as matrices with the m rows and k columns. If the users give where the m is the number of items and k is the number of rating scales, and if the users give a k star to item m, the corresponding entry is set to 1. And then we can get a 3D tensor as the input, and we can feed the 3D tensor into the model, and we use the Ciano and the blocks to implement the code, and so we can use the tensor dot, which is provided by the Ciano, and to do some mini batch processing. So because the number of rating data is much smaller than the total number of the items, so there's a lot of computation resources wasted for this kind of implementation. So we should focus that the complexity of the model is this one. So there's still some room to speed up the implementation, right? So now I will show you the visualization of the model. On the movie lens dataset, we learned the representation of the movies using the CFNAME model, and then we reduced the dimensional to 2 using the TSNE methods, and then we can plot the movies into the 2D figure. And in this figure, the yellow lines correspond to the documentary movies, and the blue lines corresponding to the children's movies. We can see that the yellow one, the documentary movie, will appear on the top of the figure, and the blue lines are in the bottom of the figure. We didn't draw all these movies into the figure because movie lines, usually one movie will have 3 or 4 or even 5 different runners, and so if we draw them together, there will be a big mess because one pawn will have several labels, and so there are some different interaction between this one. But the documentary is quite different from the children's movie, so we just show that the model can learn very meaningful representations. And this is also example for the learned representations. So the leftmost columns is the input movie, and we use the learned representation from the CFNAME to find the top 5 most similar movies using the cosine similarity. And we can see that the most similarity movies correspond to the Star Trek 4. All these top 5 is the Star Trek series 3, I think it's 1 or something like that. I'm not familiar with Star Trek, but I think that is a good example to show the model can learn very well meaningful representation. And also the second row, the input is the Sleepless in Seattle. It's a romance movie, very famous. And all these movies are the romance movies, for example, The Ghost, The Notting Hill, or The Pretty Woman. And the Lion King is an animation, and all these movies are the Lion King's are the animation movies. And for example, the Beauty and the Beast, and the Little Mermaid, the Bard's Life, and the Lady and Tramp. Okay, I will mention that actually the 6, I will show the top 5 most similar one. Actually the 6 and 7 one also the similar. I think the 6 most similar movie for the first row is the X-File. It's also a scientific movies. So in conclusion, we propose the CFNet model, and it is a quite efficient and powerful architecture for CF tasks. And the shared parameter trick is a good way to improve the performance, and we can get better scalability by factorize the connection matrix by a product of 2 low-rank matrices. And the model can be extended to a deep version, and deep version can improve the performance even better. And the proposed ordinal cost is quite useful for the CF tasks, and the model can learn very meaningful representations. Okay, so in this work we just want to see whether we can use the recent progress of deep learning to do some collaborative filtering tasks. But the test set is just the explicit feedback, right? So in practice, for example, in Hulu, we do not have a lot of explicit feedback data. So we want to develop some implicit version of the CFNet model. That is the watch count or the search history of the user, and we want the model can also exploit this kind of information. So to do this work, we propose the implicit CFNet model. That is, we model the C is the confidence of the rating, and T is the like vector, for example, whether the user liked the item or not. And we can model the condition nodes of this one in this way, and where the C and the T and the C is computed in this way. If the R is the number, the watch count or something like that, if the user watched the movie more than 1 time, we think the user will like this movie, and if not, we will it's 0. It will do not like the movie. But if the user never watched the movie, that means that he didn't like that. Maybe he just didn't aware the existence of the movie. So there's a corresponding confidence. So this method is quite similar to the implicit matrix factorization, which has been developed in the Spark machine learning library. But we use the same inspiration of the implicit matrix factorization into the CFNet model, and the condition node is computed in this way and this way, and training objective we add some confidence into the cost function, and we are developing these methods in the Hulu's dataset, and the experiment showed that the model can also learn very meaningful representation, and it can help us to build the relevance table to do our recommendation task, and we will combine the matrix factorization method and the implicit CFNet model together. Yeah, that is the feature work. So thanks very much. That is all.
So I think we have time for a few questions.
Hey.
Could you talk a little bit how you deploy this model in production?
Yes. As I mentioned in this one, actually I have put the corresponding paper on archive. If you like, I can send the link of that one. That is, we count the watch count for each of the users, and then that is the R in this equation, right? And if the R for all these movies, if the watch count is higher than 1 or higher than 0, something that is non-zero, we define that the user like this movie. And if it's 0, we define that the users dislike the movie. And the number of watch count corresponding to the confidence of the like or dislike. So that is the vector of the C. And so in this situation, that is the input of the self-name model. And we want to model the condition of the T vector given the C, the confidence C vector. And the probability of the each of the conditional is computed in this way. And so this is just so we can formalize the model in that one. There's some details about how do we. So there's a alpha. Alpha means the controls the ratio that what is the watch count corresponding to the watch count on the confidence. And usually we will set alpha equal to 300 or something like that. And then that is the equation of this model. We can train the model to get some representation and to make some predictions. So that is what we did in the production. Right.
Well, I have a question. How do you handle a cold start problem?
Actually, this work is not focused on to cope with the cold start problem, but one of the advantage of this model over the matrix factorization model is that if we have trained the model and the user have some new behavior, we do not need to retrain the model to incorporate the new behavior of the users. We can just add the corresponding ratings, the corresponding parameter into the hidden representation, and we can directly compute the probability of the user, the rating, right? So I mean, for this model, we do not have a representation of the users. All we have is the representation of the movies for each of the rating data, right? So we just add the new behavior, the new movie and new ratings into the consideration and compute the hidden representation. So the model can be updated. So we do not need to retrain the model. So that somehow can solve the cold start problem, but it will not totally solve this problem, but it's a little bit one step better than the matrix factorization.
So in practice, how often do you have to retrain this both in your online state and your offline state?
Actually, so for this work, I use the Ciano and the Block to train the model, but the Ciano is not very efficient. So in the production for this work, I use the TensorFlow to train the model, and because we do not have a K scale, we just have 2 scale, the number of parameters will not be that much, and so the code actually is quite fast. I think within several hours we can we can train the model with a very good precision and use that in the production.
Any other questions from the audience? Oh, yes.
Hi.
How does accuracy scale for ratings?
Sorry?
How does accuracy scale for ratings?
Scale the number of ratings?
So as you get more ratings, how much more accurate does it get?
I think it can be explained in this table. For the movie lens, for the Netflix data set, there's much more ratings, and so the accuracy comes with over the other data R's will be much better. So more data, the advantage of the model will reveal have much more power to model the big data.
What about the user level?
The user level? Actually, we didn't measure the user level in our product. We just show the advertisement, and in our product we use before the A/B test we use the MPR, the mean percentage, something like that. I don't remember exactly the name. That is a recall-based method, and we also found that the model can if the reading data scale up, the model can also get even much better than the matrix factorization method. That is the only baseline we compare with for the implicit self-name model.
For the implicit model, how do you incorporate multiple user behaviors?
Multiple user behavior. You mean
Something like watch, right?
Okay, so for the implicit model, so far we only count for the watch count information. But the watch count information is just a kind of data information source. We can also use the search or something other methods and to build different reference table or build different representation based on the different similarity and combine them together. Within Hulu, we have also a method which is something like the active learning method. We can combine different representations together to get an example to which one is more important or which one is not that important, and to merge them into a uniform representation and use that in our final product. So that is also used in our group. I think you have a question?
Yes. So the actual winner of the Netflix prize had a test RMSE of 0.8567.
Yeah.
How do your results correlate to those numbers? I mean, do the numbers that you have on the screen, are they on the same scale? Is what I'm asking.
Yes, that is a good question. So the Netflix challenge has closed about 5 or 6 years ago, right, in 2009, and because some privacy problem. So we can't find the test set of the data set of the Netflix data set. And what people usually do for this data set is that we split the training set of the Netflix challenge into 2 parts. One is 90% and one is the 10%. And we do 5 different split of the data set and to report the mean value of the test RMSE. So I think we can't directly compare this model with the Netflix data, with the winner, the Netflix winner. But all these baselines, for example, the auto-right or the local low rank matrix approximation, they also use this kind of comparison. I have confirmed the comparison is strictly fair compared to the other baseline, so that will make sense. And because the RBM in the Netflix dataset challenge, the report is the 0.89 or 0.88, somehow like that. And because we get a very big improvement over the RBM and under the same configuration of the dataset, so that will also confirm that our method is much better than that one. Thanks.
Any more questions? All right, it's like that. Thank you. Help yourself to some more food if there's left, and then use the same elevators you came up in to head back down. I think there's parking
to improve the performance. So I think you will learn more by my paper than that paper. So just to clarify. Okay, so I will start my talk. This talk, this is the outline of this talk. I will first introduce the motivation and the related work. And then I will introduce the basic model of CFNet and the 2 tricks to improve the performance of this model. One is the sharing parameter between different ratings, and the other one is to factorize the big connection matrix by the product of 2 low rank matrices to have better scalability. And I will also introduce an ordinal cost, which is quite useful in collaborative building, and to my best knowledge, we are the first paper to propose this kind of ordinal cost for the CF tasks. And I will also tell you how to extend the CFNet model to a deep model to have better performance. And in the experiment parts, I compared our model with the other state-of-the-art baselines on some explicit feedback data set. And I will also show you the visualization of the learned model and give you a quick overview about what is the feature work we are going to do in Hulu's product. Okay, the motivation. We all know that this one, This one, this one is a paper that I never know I didn't know the existence of this paper, but this one is my paper. I just searched with the title of my paper, but I don't know why Google put this one in the first. And so today I found a guy to attend this attend this workshop. He brings this paper with him, but I will tell you that is totally wrong. And actually, I think the main motivation of this paper is the same with my paper. They also try to use the NAID model. The NAID is short for the Neural Autograph Distribution Estimator. However, the guy sent this paper to ICDM about 2 years ago. But the paper was not accepted. So just put this paper on his website. But so after I know the existence of the paper, I'm so nervous. Maybe they are the same. So I have a quick look of this paper. Finally, I found the paper. Although we use the same motivation, but this paper didn't use any. They are not the same at all. They didn't use the trick, and the performance of that paper is not that good. It only compare with the RBM CF, but we compare with the richness of the art, and we also use a lot of that. The modern online service, such as Hulu, relies heavily on the recommender system to help users to identify the item that they might be interested in, and also provide the personalized experience. The most popular and the successful technique to building a recommender system is the collaborative filtering, which predict the user preference based on the user's past behavior and the decision made by the similar users. One of the basic assumptions behind the CF is that the user preference will not change dramatically in some time. CF is also the core of Hulu's recommender system, and this technique has been widely used in our product. For example, this is the home page of Hulu. Actually, we have provided a personalized home page. That is the trees is different for different users based on your preference, and also we have developed the personalized must-have. The must-have is this one. And it's very big and give you big impression about what is trending on Hulu or what is the recommendation based on our prediction. And so that is also personalized, and also the watch list, the top picks, and the rated shows. A lot of recommendation products use the CF task.
I think we're all very excited. Well, I'm very excited, at least, to hear from Yin Zheng, who received his PhD in EE from Tsinghua University in Beijing, China in 2015, and is now employed at Hulu Research over in Beijing, working on recommendation systems and deep learning. And this talk he's going to give, CFNAID, he actually presented at ICML a week ago. I attended the talk. I thought it was very good. Too short, so we're excited to see the elongated version of the talk. So please join me in welcoming in.
Okay. Thanks, Joe, and the very nice introduction. And today, I'm very glad to introduce our. I'm a researcher at Hulu's recommendation team. Today, I'm very glad to introduce our recent progress on collaborative filtering, which is called CFNAID. This work was joined with my colleague Bang Shengtang, the second one. The Wen Huiding and Eric Zhou, our boss. So before I start my talk, I just want to clarify that about 2 days ago, I found a paper which is quite similar to my paper, but I didn't aware the existence of that paper. So I just show you that one. So we'll use the CF techniques. Although there are a lot of CF techniques, CF methods, most of them are based on the matrix factorization. If you search the CF on Google, you will find some like the SVD or SVD++, the BIOS matrix factorization, the probabilistic matrix factorization, probabilistic matrix factorization, and so on. The most successful and famous neural network-based CF techniques is the RBM CF, which was first proposed by the Sarakuninov, the Min, and the Hinton in 2007 at ICML. In that paper, they used the RBM to model the probability of the ratings, and it works well in practice and also well in the Netflix challenge. To my knowledge, there's a tutorial two years ago at KDD by the Netflix guys. He confirmed that they use a combination of the matrix factorization and the RBM CF in their product. They said in the tutorial. And but you know the RBM CF is based on the restricted Boltzmann machine, so he had to relies on the contrastive divergence to optimize the model. So it will be very slow and not